15e, we are talking about derivatives of exponential functions. Now, we need to remember what exponential functions are. So they are things like y equals 2 to the power of x, y equals 5 to the power of x, y equals 0.5 to the power of x, y equals 10 to the power of x, okay, and so on. And we could have various transformations of these exponential functions, but we will just look at a simple exponential function with a base and the exponent x. And we have our very special one, the natural exponent, y equals e to the power of x. So if we take a look at our TI Nspire, so I would like you to grab your TI Nspire now. If you don't have it, pause the video and go and grab it so you can start to learn some of these keystrokes for graphing. Okay, we are going to go to the on page. We're going to graph. A few ways you can do that. Press the graph button, okay, or on page again, you can press this. Okay, so let's see that again. From the on page, home page, we can either press this graph icon down here, or we can press the B, capital B, graph. Okay, we are going to graph y equals 2 to the power of x. 2 to the power of x. Enter. And that's what this graph looks like. Now let's graph its derivative. We can do this on this graph. So we press tab. Now we'll have a second function. That second function we want to be the derivative of the first function. So we need the derivative. So to the right of the number 9 on your keypad, there's this button here, which brings up this whole list of things you can choose from. We'll deal with a lot of those later on. Here we have the derivative. Okay, so this is going to tell us we're going to take the derivative of the function that we put inside the brackets. So this is with respect to x, so we need an x there. Then we scroll over and put 2 to the power of x. And enter. All right, so here we have another function. So the blue function is our, let's move that up. The blue function is our 2 to the power of x. The red function is the derivative of 2 to the power of x. All right, what kind of a function is that derivative? Okay, so I want you to think about that. What kind of a function is that derivative? Okay, we're going to come back to this and we will do another example. Okay, we're going to add another graph. So y equals 5 to the power of x. Another exponential function. Graph it. Enter. Let's see what the derivative of this is. So tab, that little button to the right of the number 9. We want to select the derivative. Okay, it's with respect to x. So we put an x there, scroll over, and enter 5 to the power of x because that's the function we're taking the derivative of. Enter. Okay, and again, blue function is 5 to the power of x. The red function is our derivative of 5 to the power of x. So think about what kind of a function this is. Okay, so I hope you would have thought that both of these derivatives are actually exponential functions again. Okay, we ended up with exponential functions both times. Let's talk a little bit about what this derivative function means. Okay, so if we take a look at this point, the y-intercept on our function, that y-intercept is 0, 1. On the function, y equals 5 to the power of x. The slope of the tangent at that point, we're told what that slope is in the derivative function. So if we go up to where 0, x equals 0 on our derivative function, then that's approximately, we could trace and find the exact amount, but that's approximately 1.8 maybe. Okay, so that means that down here at this point, the slope of this tangent to the function y equals 5 to the power of x is approximately 1.8. Okay, so we saved that one as document 2. All right, third one. Let's take a look at the natural exponent. So e to the power of x. Now when you press the e button, e to the power of x button, that little box shows up as in your exponent position already. So we just put in x, so e to the power of x. There we have e to the power of x. Remember, e is just a number, 2.7 approximately. And so this is just refers to the base of that function. Now, if we take the derivative of this function, so tab, find that derivative button with respect to x. So e to the power of x. Enter. This is the exact same function as what we started with. Okay, this is very, very important. So this function lies right on top of itself. So the derivative of e to the power of x is obviously e to the power of x. Okay, and let's take a look at why that would be so special then. If we take any point along here on the actual function, our original function, so let's choose 0, 1. That means that the slope of the tangent at that point is given to us by the derivative function, and that y value is 1. So the derivative, the slope of the tangent at this point is 1. If we look at 1 and e, the point 1 e, so 2.7, so roughly here. Okay. If we take a look at that, the slope of that tangent would be e. And down here, the slope is 1. Okay, and so on. So this is a very important concept to understand. All right, so looking back here, we have these functions, and we need to be able to take the derivative of them. All right, now, honestly, we will probably hardly ever be even looking at the derivatives of these types of functions in calculus. We will be, however, dealing with e to the power of x a lot. Okay, but I want you to know why e to the power of x, the derivative of it, is still e to the power of x. The way we take derivatives of exponential functions is a to the power of x. Okay, so a being any base whatsoever. The derivative of that is a to the power of x times ln a. Okay, ln a is just a number. Ln a is just a number. Okay, so in other words, we have this same base function, a to the power of x, but it now has this constant number multiplied by it. In other words, it has a stretch factor. So, given this, if we look at y equals 2 to the power of x, the derivative would be 2 to the power of x times ln 2. And ln 2 is just a number, a constant number. So that means that when we looked at the graph y equals 2 to the power of x, and then we took the derivative of that graph, we also ended up with an exponential function, but it was a transformation of 2 to the power of x by a stretch factor of ln 2. Okay, likewise, derivative of 5 to the power of x will be 5 to the power of x multiplied by ln 5. Ln 5 is just a constant number. Okay, so that's why when we graphed that function and then graphed its derivative, it was still an exponential function. It had a stretch factor of ln 5. Okay, so on and so on here, the derivative of 0.5 to the power of x will be 0.5 to the power of x multiplied by ln 1/2. And the derivative 10 to the power of x, 10 to the power of x multiplied by ln 10. Okay, this brings us to the special one, y equals e to the power of x. The derivative then, following this same rule, would be e to the power of x times ln e. But let's think about the number ln e. Okay, using that little trick we talked about last year, log base a of a to the power of x equals x. Okay, this is log base e of e to the power of 1. So that actually just is the number 1. So therefore, the derivative of e to the power of x is just e to the power of x. We're going to use this time and time again throughout the course. Okay, getting into something more complicated then. If we have y equals e to the power of some other function. So for example, we may see y equals e to the power of negative x, or y equals e to the power of 2x plus 3. Okay, what we will do here to find the derivative is the rule states this will be equal to itself multiplied by the derivative of that function. Okay, very important to remember as well. So here in this example, we will have e to the power of x, e to the power of negative x, multiplied by the derivative of negative x, which is just negative 1. So negative e to the power of negative x. And over here, the derivative itself multiplied by the derivative of 2x plus 3, which is 2. So 2e to the power of 2x plus 3.